Hi everyone, welcome back to another Pre-Calculus 12 video. Today we are doing Chapter 4, which is on radicals, and we're starting with 4.1, but in an attempt to shorten the videos a little bit, I've split it up into Part 1 and Part 2. So what you'll find, I've been sort of doing this throughout the year, is that I like to go back to the basics and use the basic graph to help us to determine what the more complicated ones are going to look like. So just at the start here, I've done some basic review from things that you've learned in the past. If we have the basic equation for radicals, it's f of x equals square root of x. So that's this here that we're looking at. And if we want to look at a basic graph of what that looks like, we would have 0, 0 on there. So again, this is like saying y equals root x. If I plug in 0 for x, we can see that y is going to also be 0. If I plug in 1 for x, well, the square root of 1 is 1, so that makes sense. And if I plug in 4 for x, square root of 4 is 2, so that makes sense as well. So you can see that I've strategically picked, I went from an x value of 1 all the way up to an x value of 4 because all of the numbers in between are not perfect squares. So I'm strategically picking perfect squares because having a perfect square in there is the only thing that will allow me to work with whole numbers for my y values. So it's good to have 0, 0, 1, 1, and 4, 2 as my basic points to refer back to as things get a little more complicated. The next part, I'm just quickly going to show you this. Radical notation, x to the n equals a, and if we want to rearrange that and write it as a radical, so this is an exponential form. If we want to rearrange that and write it in radical form, so algebra is all about opposites, if I do the opposite of that, then x would just be the nth root of a. So basically I would be taking the nth root of this side in order to get rid of it, and then I'd also take the nth root of this side. So that's how we're coming up with this part here. And again, I'm a big fan of showing you with actual numbers and examples, so I've tried to color code it so that you can clearly see where it's coming from. 2 to the 3 we know is equal to 8, and if we rewrite that in radical form, like over here, then the cube root of 8 is also equal to 2. So it's just showing you opposites, just like if I multiply a number by 5 and then I divide it by 5, they're complete opposites of one another. Similarly, these are opposites. And then just some quick vocabulary stuff. I'm not going to spend time on this. You can read through this on your own. You don't necessarily need to know this, but it's just good to have a little bit of background sometimes. So I will leave you to reading through that and looking at that yourselves. And we'll dive into the first example. Solve the following for x, which is a real number. So we're starting off nice and easy with things that you've done in the past. Algebra, again, is all about opposites. So if I want x, then we know that we would square root both sides. So x would be equal to, I would say 2, but technically speaking, we should say plus or minus 2, because negative 2 times negative 2 gives us 4. And so does positive 2 times positive 2. We're going to fly through these because you already know these. If we have x cubed, the opposite of that would be me cube rooting that. And then that means I also need to cube root that. Well, cube rooting something that's cubed just cancels it out like that. So I'd end up with x here. And then if I take the cube root of negative 125, well, if we take the cube root of a negative, we know the answer is a negative, and it would be negative 5. So negative 5 times negative 5 is positive 25. Positive 25 times negative 5 again does give us this. So that's the thought process for going through this. And then we get to something like this. I need to take the fourth root of x, and then I need to take the fourth root of 3. Clearly, that's not going to give us a whole number. So you'd have to punch this into your calculator. Punch in the fourth root of 3, and you can either show this, it's going to be an approximate value for our answer. You can show it with a squiggly equal to sign like this, or an equal to sign with a little dot at the top, they both mean approximately equal to. And when you punch this into your calculator, you should get around 1.32. And again, I should say that it's plus or minus because of the fact that we have an even root there. Notice I didn't do that for part B when I had an odd degree root. Okay, so then if we move on to this one, I would need the fourth root, but I can't take the fourth root of a negative. In fact, I can't take an even root of a negative value, so I can't solve this. It's an imaginary number. So we're only looking for real numbers. This is not a real number. It's an imaginary number, so I can just leave it with this symbol here to show that that's not going to happen. I'd take the fifth root of this and the fifth root of this, and when I do that, x would be, this time I'll use a squiggly equal to sign. That's not the correct terminology, but it works. So it's approximately 1.25, and if I take the fifth root of a negative number, that is allowed, so these two cancel, so that I get x, and that is allowed, so I would get approximately negative, because if we're taking the fifth root of a negative, the answer is going to be negative 1.25. So there's some quick warm-up to get us into how to do this stuff, and then we'll take a look at graphing transformed radicals. So in the red box here, we have our basic form, our basic radical equation, and I, as a theme throughout the whole course, will refer back to the basics. So it's always, anytime anything looks super complicated, like this thing here, this is with all of the possible transformations applied to it. So this is, again, us going back to chapter 2 that we looked at. And then the red box is just completely basic form with all the transformations stripped away. So let's slowly go through what this would look like. If I have y equals root x, well, this is the one we started with those points 0, 0, 1, 1, and then 4, 2. So that's basically what that would look like. And then this, again, is review of the transformations chapter. If I have a negative sign here, I would ask myself, does that affect the x values or the y values? Since it's in under the root sign with the x, I know that whatever my x values were, it's going to flip them over the y-axis. So it, in fact, ends up giving me the same as part A, but just flipped over the y-axis. That's the impact that negative sign has on my graph. And then for part C, notice that the negative sign, I've purposely done them side by side so you can see the subtle differences. The negative sign is on the outside. So it's actually affecting my y value. So I like to always ask that guiding or leading question. Does this affect my x values or my y values? And it's my y values. So I would take what was my original graph and I'd flip it over the x-axis. So I, this time, end up getting this. And I'm going to get rid of the dotted part that I was showing you as the original. My graphs are kind of not looking great. Like, it's more like that. That's a bit better. And then for the last one, that's affecting my y values and that's affecting my x values. So I would take my original and I'd flip it over the y-axis and then over the x-axis. So I would actually get something that looks like this, which is in quadrant 1, 2, 3, just to sort of recap. So here I've just quickly written out what the impact would be, flipped over the x-axis, flipped over the x and y-axis. And I've already written out what the domain and range would be. You can go through and have a look at those, but that's a review of what we've done before, so I'm not going to spend much time on that. But if you like, you could at this point pause your video, have a look at the domain and range listed at the bottom. So that's this stuff here for each of them, and just ensure that you understand where that's coming from. Okay, so having gone through the reflection part of it, let's take a look at the impact that this transformation would have on our graph. So if we have, well, maybe I'm going to draw it dotted again. That would be my basic graph if I had just y equals root x. So basically I'm looking at this +2 and asking that same leading question, does that +2 affect my x values or my y values? It's in there embedded with the x, so it's affecting my x values. And we know that for x, we take the opposite of what we see. So if it says x plus 2, I'm actually moving my starting point to minus 2. So I'm going to actually have my dot right there instead. And so I still have the same shape. Nothing has happened that would change my shape. I'm going to erase that or get rid of it. And basically I'd have a graph that looks like this. And to show you the impact that this would have, I would again start with that leading or guiding question. Does this minus 3 affect my x values or my y values? It affects the y values. So what would have been my original graph here, it actually takes it and moves it down 3, because when it's y values, we take it as we see it because the y is isolated on the left. And with x, we take the opposite because the x is embedded within the equation. So I would go down here instead to minus 3, and my graph would end up looking something like this instead. Perhaps I haven't drawn that well, but it would go kind of like this and would eventually cross. And we could figure out the details with where it's going to cross, of course. That's where y would be equal to 0. We could plug that in, etc., etc. But this gives you at least a general sense of the impact of these transformations. To be specific or accurate, that's a translation 3 units down, and this one was a translation 2 units to the left. Okay, so let's take a look at the impact that a stretch is going to have. So remember, we looked at the impact of stretches. Well, it's not asking for this root x part, but I've purposely put them on your graph in black so that we can use that as like the referring back to the basics so that we can see the impact that this 3 is going to have. And then we're going to look at strategies to figure out what's happening. So I would ask, does this 3 affect the x values or the y values? It's right in there with the x, so I know it's affecting the x values. And I know that with x it's the opposite. So I know that it's a horizontal compression by a third. So I would multiply my x values by a third. So what that means is it's going to reach the same y values a lot quicker. So what it's doing is it's taking my original root x graph and it's sort of compressing it this way to a third of where it was. So whatever this y value is here, it's going to actually reach it at about a third of the x values. That's what this is saying. So the 0, 0 will still be there, but basically we end up getting a graph that's like a little bit, it looks either higher if you want to say, or like chunkier looking, because we're taking the original and we're squishing it in like this. So as we compress it horizontally like this, it's also naturally going to vertically impact it as well. So it's vertically expanding it by 3. So that's ultimately what it's going to look like when we look at the comparison. And then if we do the opposite here, notice that this is 1/3. So this would be a horizontal expansion by 3, because with x values, it's always the opposite of what we see. So if we have a third there, what this is saying this time is that if it's a horizontal expansion by 3, it's stretching it out. So if I compare it to my, like, using the same approach as I did with the last one, whatever this y value is here, it's going to take me 3 times the amount of time to reach that y value. So it basically stretched it out like that. So it's taking much longer. So this is like, if you want to look at it this way, that's a third of the way, 2/3 of the way. So it takes 3 times as long to reach the same height, is one way of looking at this. Okay, so hopefully going through those basics will help us to put it all together, which is what we're doing in this last example. So we want to use a strategy or an approach that simplifies things a little bit. So there's a lot going on here, but I've showed you strategies when we did the transformations unit, or the chapter 2. We looked at methods of cleaning something like this up to make it nice and easy to pick out what the transformations are. So I'm having some issues with how this is written. We like to start with x. So the first thing I need to do is I need to factor this out and clean it up so it looks like something that I'm able to easily work with. So I still have that 2 there, but inside the radical sign here, I can factor out the negative and then rearrange the 4 and the x. So that becomes positive x, and then that's going to become minus 4. And the rest of it is still plus 1. So I haven't changed it a whole lot. I just basically rearranged this so that I can easily pick out what exactly is happening and be able to quickly apply it. My next thing that I like to do, especially when it's complicated and there's a lot of stuff going on, I like to go back to the basics. So I like to look at this and compare it to just a basic graph, which would be y equals root x. And in y equals root x, I'd have the points x, y. But that becomes, or maybe I'll do that here, it's not xy, it's this. So the xy, I'm going to look at like what it becomes by doing this. I'm going to pick out all the transformations. There's a 2 there, there's the minus sign there, there's the minus 4 there, and there's a plus 1 there. Oh gosh, I'm not color coding it. I will do that. So if I'm looking at the x value, I'm going to use green to talk about the x value. So I want to pick out all the stuff that's going to affect my x values. That would be this part here and this part here. The rest of it doesn't affect x. So what this is saying is instead of x, the negative means that I'm going to have negative x. And if it has minus 4 here, that means I have plus 4. So this is what I am doing to the original point that would have been on the original graph. Some examples of original points that would have been on the original graph is, remember we talked about them, 0, 0, 1, 1, and 4, 2 are just like if I were to do a table of values, these are quick, easy points that would be on the original y equals root x basic graph. So that's what I'm using there. And this is telling me what to do to those points, what to do to the x value of those points. I want to do the same thing with y. So the stuff in blue is affecting my y value. So, with y, I take it as I see it. So if I used to have y, I'm now going to have 2y plus 1. So this is what we are doing to the y values. So in order to make sense of this, I'm going to take my point 0, 0, and I'm going to come up with a new point. If I had 0 and I plug it into here, I'd just get negative 0 plus 4. So my x value becomes 4. If I take my y value of 0 and plug it into here, I'd have 0, because that just wipes it out, plus 1. So I'd have the point 4, 1. I'm going to do the same thing with this. I'm going to take x value of 1, so negative 1 plus 4, so I get 3 here. And I'm going to take my y value of 1, and I'm going to plug it into here. So I'm going to do 2 times 1 is 2 plus 1, so I also get a 3 there. Okay, I'm going to do the same thing here with the 4 and plug it into, I'll try to show you with a different color, but I'm running out of colors here. I don't know, I'll take this 4 here and I'll plug it into here. So I get negative 4 plus 4. So you can see that my value becomes 0. And then if I have the 2 here and I plug that into here, it would be 2 times 2 is 4 plus 1 is 5. So you can see the process or the method that I'm using. I like to go back to the basic graph, pick out a few key points, look at the transformations or what they're going to do to the original point, and then apply it to some of the basic points to see what they become. So now graphing this out becomes a lot easier. If I go to graph this, well, 0, 5, I know that that would be there. 3, 3. Okay, well, 1, 2, 3, 4, 5. 1, 2, 3. So I'll make that there. 1, 2, 3. It's going to be around there. And then the point 4, 1. So there's 4, there's 1. So you're starting to see that we have a graph that, oops, it's looking a little shaky, but you get the idea that that's how we figure it out. You have knowledge about transformations. So you can take a look at this and double check, like, does this make sense? That negative sign tells me there should be a reflection over the y-axis, and that's happening. It's moved over 4 to the right, and that's happening. It's up 1, that I can see on my graph. And then the stretch I can see as well, so I know that this is good to go. So I hope that that is helpful and brings you some clarity on what to do with this. Here is your suggested work for the day. Of course, this is your suggested work. If you are up for it and want to do more, you can. It's just that there are some portions that I will be going over in the next video, which I will be assigning along with that. And that's it.